Hello and welcome back to question 3 for the 2019 Level 3 Aqueous Chemistry paper. So this one should be about acids and bases and buffer solutions. So question 3, two solutions of equal concentration were prepared, one of ethanoic acid and one of ammonium chloride. They give us both the pKa values. So explain which solution will have the lower pH. So first things first, we need to understand what is the Ka value defined as. Ka value is the definition of the acid dissociation constant, and that refers to how far or how much of the acid will dissociate to give you its ions, which in this case would be the conjugate base and hydronium ions. So the larger the Ka value, the further extent of dissociation of that particular acid, so the stronger it is. So we know that Ka is equal to 10 to the power of negative pKa. So therefore, CH3COOH has what I just call ethanoic acid. So ethanoic acid has a higher Ka value than NH4 plus. So in this case, we know that Ka of so just write down that we say that Ka is the acid how much will dissociate to give the conjugate and to give the conjugate base and the hydronium ions. So they can say the higher the Ka value, the higher the Ka value, the higher the. So we can say the bigger the Ka value, the higher that the more of the acid that's going to dissociate, so the more acid particles. Hence for a stronger acid. So we can say that Ka, we already said that at the top, we don't need to say it again, so we can just say. So therefore, we can just say that ethanoic acid is the stronger acid for this question. So we can say, we can mention that it will dissociate. Then NH4 plus will to form NH3. Yeah, and that's all we need to say for this question, okay? So we can say that CH3COH is the stronger acid. Evaluate the electrical conductivity of ethanoic acid and NH4Cl. So this is a pretty standard question. Okay, electrical conductivity depends on the relative concentration of free moving ions in the solution. NH4Cl is a solid which can which can dissolve to form NH4 plus and Cl minus in water. So therefore, there is a higher concentration of the free moving charged ions in the solution. Therefore, NH4Cl is going to have a good electrical conductivity. CH3COH, which is ethanoic acid, is a weak acid and therefore will only partially dissociate in water to form CH3COO- as well as H3O plus ions. So therefore, since the relative concentration of ions is very small for the solution containing ethanoic acid solution is going to have not very good electrical conductivity, or we say it's a poor electrical conductivity. So we can say that CH will so we can say that most will remain as CH3 or OH particles. So we can say the relative concentration so the overall relative concentration is low. Therefore, since electrical conductivity, I'll just abbreviate it as EC. So since electrical conductivity depends on the concentration of the free moving ions. Since electrical conductivity depends on free moving ions, CH3COOH will have a pore. And we can write an equation to represent why, to represent the dissociation of CH3OH. So we should have water. So we can say NH3 plus NH4Cl is an acidic salt and will dissociate fully. Dissociate or dissolve fully in water to form NH4 plus ions and Cl minus ions. So we can say NH4 plus will further react to form NH3 and hydronium plus, and that's reaction with water. However, the overall concentration is still high. The overall ion concentration is still high. So hence NH4Cl solution has a good electrical conductivity. Okay, so we have a high, so therefore we can say NH4Cl, that's going to give us NH4 plus Cl minus. Alright, that's all we need to say for this question. So we can just say that NH4Cl has a good electrical conductivity and ethanoic acid has a poor electrical conductivity. Alright. So looking at question III, the ethanoic acid solution has a hydronium of 1.78 times 10 to the power negative 3 mole per liter. Calculate the concentration of the ethanoic acid solution. Okay, so in this case, we've got the pKa, so we can find the Ka. Yeah, so pKa is 4.76. So therefore, Ka is equal to 10 to the power of negative 4.76, which is equal to 1.7378 times 10 to the power negative 5. And therefore, we can write the equation for the dissociation of CH3COOH. And we can express this in a acid dissociation, not acid dissociation. We can express this in the equilibrium expression. So we can say that Ka is equal to concentration of CH3OO minus times hydronium divided by CH3COOH. So we're going to say assume little change, So therefore, we can just say that it's equal to the original concentration of CH3COOH. So therefore, we can say that what am I saying? Saying that we can rearrange to find CH3COOH. So that will just be this divided by Ka. However, we know that for the 1-to-1 ratio, so 1 mole of ethanoic acid is going to give us 1 mole of the conjugate base and the hydronium ion. So therefore, the concentration of hydronium is equal to the concentration of the conjugate base. So therefore, we can say this conjugate base is equal to hydronium. So therefore, the concentration of CH3COOH is equal to 1.78 times 10 to the power negative 3 squared divided by the Ka, which is 78 times 10 to the power. Alright, so therefore that should give us the concentration is 0.182 mole per liter. Alright, looking at BI. Dilute hydrochloric acid is added to a solution of sodium ethanoate until the ratio of CH3CONA to ethanoic acid in the solution is 2:5. Calculate the pH of the buffer solution. Alright, so for this question, we're adding HCl and CH3CONA. Okay, for this question, we have CH3COONA. It's going to give us CH3CO minus and Na plus. So at equilibrium, we're going to have both CH3COOH and CH3COO minus. And we know that this is in a 2:5 ratio. So for every 2 moles of CH3CO minus, we have 5 moles of CH3COOH. So we don't have to write it down. We can just say ratio is 2:5. So therefore, we can say that the concentration of CH3COO minus divided by the concentration of CH3COOH is in a 2:5 ratio, which is 2/5. So therefore, we can say 5 times of the CH3COO minus concentration equals to 2 times the CH3COOH concentration. And we're going to come back to the Henderson-Hasselbalch equation, so that's our pKa equals to pH plus log of the acid over the base, concentrations of course. And this is the equation for a buffer solution. So we have both the conjugate acid and the base. So therefore, we're going to be able to find the pH because we know that the pKa of the acid we were given, it was 4.76 if I'm not mistaken. Yes, 4.76. So therefore, we can say 4.76 equals to pH plus log of the acid, which we'll say is the acid was the acid we can rearrange this equation. That equals to 5/2 times of the concentration of COO minus. So we can say that 5/2 times of CH3COO minus divided by concentration of CH3COO minus. They will cancel out, so we just get log of 2.5. So log of 2.5 and then pH therefore equals 2. That is equal to 4.36. Alright, that's question done as well. Question number II. Explain why this buffer solution will be more effective at resisting a change in pH when a small volume of strong base is added rather than strong acid. Your equation, your answer should include the equation. Okay, blah, blah. Alright, so a buffer solution is one that contains both the acid and the conjugate base. So just to simplify it, I'll just say it contains both the acid and the conjugate base. So in the current buffer solution, we can say that our buffer can resist changes to pH for small volumes of added base or added. Okay, so in the current, we have both CH3, both ethanoic acid and the conjugate base. And if we go back, it said that there was a lot more conjugate acid, which is in the current solution. Is much greater than the concentration of CH3COO minus. So therefore, when added base in the solution, it will react with it will be neutralized by the CH3COOH. Will be and when acid is added, it will react with. So we can say since the concentration of ethanoic acid is much greater than a conjugate base, which is ethanoate, which is okay. It's much greater than CH3CO minus. The buffer has more CH3COOH available to react with base and less less CH3CO minus that can react with the acid. Hence, the buffer is more effective at resisting changes for base. Sorry. Right, that's all we need to say for that question. Okay, it's a bit wordy, but okay. How would the pH of the buffer solution be affected when it's diluted with water? The answer is that it is not affected by water, since by adding water, and that's because both of the conjugate acid and the conjugate base will change, or the concentration will change by the same factor. So we can say. So we can say the ratio of the concentration, of the CH and the CH3COO minus does not change. Therefore, there is no change in the pH. Alright, so that's all we need for that question, and that's it for the 2019 Level 3 Aqueous paper. I hope you enjoyed watching this video, and I hope to see you all in the next one. Thank you, bye.